Então, vamos começar?
Uhum. Podemos.
Então, o último palestrante do dia é Ciro Campolina, do Instituto de Matemática Pura Aplicada, aqui, né? E vai estar falando de incompressible fluid flows on logarithmic lattices. Ciro.
Okay, thank you, Milton, for the presentation, and thank you, Annie Beonzi, for the very kind invitation in the name of the organizers, of course. And this is a joint work with Alexei, also from IMPA. He's also taking part on this event. I think he's going to present next week. And we are going to talk about incompressible fluid flows on logarithmic lattices. So just to give a context, we are in a more general perspective, we are dealing with multi-scale nonlinear flows and the dynamics, like the global regularity of Navier-Stokes equations, finite time singularities in viscid flow in three-dimensional compressible water equations, vanishing viscosity limit, anomalous dissipation, intermittency in Navier-Stokes turbulence, and many others. And some of them were already addressed in this workshop. But all of them share some common difficulties, and they are essentially the nonlinear behavior of the equations and the fact that they have multi-scale dynamics. So they range a very broad range of scales, since the inertial and the finer ones on the dissipation range. And because of that, those fine scales are inaccessible to computational techniques. So if you want to investigate besides analysis, if you want to investigate for a possible answer, it's very difficult to do it through numerical simulations. So just to summarize two common techniques of investigation of those problems, besides mathematical analysis, we have direct numerical simulations, which consists in taking the full equations and choosing a numerical scheme and then simulating them on a computer. And the pros is that we have access to solutions. Of course, they are approximated solutions, but they are solutions of the full model with no simplifications in the equations. But because this is a very expensive task, they can only reach not so small scales. So usually 10⁻⁴ scales with respect to the larger one. While the finer scales than that, they are not resolved, right? And facing this difficulty in numerical simulations, we may try to simplify the equations before simulate them. And this is what I call simplify models. So you take part of the equation, you simplify it, and then you solve computationally. And because of the simplifications, we have access to very fine scales. But again, we have troubles because the simplification of the equations may depart from the original model, and you may lose some important properties of the original phenomenon. So we have these two approaches to try to find answers for those problems, and somehow they don't fit what we need. So what we propose here is to find an intermediate approach to interpolate these two things, and to find some technique to obtain simplified models, to simplify in some way. But still very close to the original model, but allowing computations, numerical simulations. And what we do is to introduce a new technique, and through this technique we construct simplified models, but they still retain the exact form of the equations. So how do we do that? We don't change equations. We change the domain at which it is defined. So we consider exactly the fluid dynamics equations in their exact form. But instead of simplifying the equations, we change the domain. So in direct numerical simulations, we would use regular grids. So we have, for this example, a two-dimensional picture. And instead of using this regular grid, we use this more sparse one, which is what we call by a logarithmic lattice. So what is a logarithmic lattice? We choose a factor, which is lambda, greater than 1, and we take integer powers of this factor and consider, for example, if lambda equals 2, then we have lambda 2, 4, 8, 16, 32, and so on. And this is the two-dimensional picture we have. So what are the advantages of using this logarithmic lattice? First of all, they are scaling invariant. So if we take a point of the logarithmic lattice and rescale this point, it is again on the logarithmic lattice. And this is very important for the study of such flows because they are all very related to the interplay between scales. Because of that, equations retain their exact original form. So we don't change the equations themselves, only the domain at which they are defined. And as a consequence, symmetries and invariants, they are preserved. And we have also the computational advantage that with only a few nodes, we already span a large spatial range. So while for direct numerical simulations, we only span 10 power minus 4 of scales, here we can reach way finer scales. So even for three-dimensional simulations, we can reach 10 power minus 12. So we have this computational advantage of taking all the properties, the most important properties of physical properties of the flow, but still allowing very fine simulations. Okay, so we changed the domain, but we need also to make sense of the equations in this new domain. So this is these are the operations on the lattice. All functions now are defined as a function of the wave vector on the lattice and time. We have all of them should satisfy reality condition, and this is because they are mimicking functions which in physical space they are real valued. Spatial derivatives in Fourier space, they are Fourier factors, so it's just multiplication by k. And the product between two functions, the nonlinearities of the equations, they are convolutions, but those convolutions should be restricted to the lattice. So if you have the product of two functions at point k, they should be a sum of points u, v at p and q, and p and q summing up k, but p and q should be on the lattice again. So we are decimating and making a convolution restricted to the lattice. And by those 3 points coupled by this product, we call it triads. So the triads are the triple of points, p, q, and k, on the lattice that sum up. Okay. And here we reach to the first methodological problem here, which is the fact that logarithmic lattices, because they are powers of integer powers of fixed numbers, they are not closed under addition. So if I take general p and q on the lattice, they don't necessarily sum up on the lattice. So we need to classify all possible triads for this product to be non-trivial. And we do it, we have a theorem for that. We classify all possible non-trivial lattices through the parameter lambda. And it turns out that for sufficiently large, not so large, but sufficiently large lambda greater than 1.05, the non-trivial lattices are described by these 3 parameters. These are the representatives of the 3 parameters. So we have very special numbers from number theory. So the first one is lambda equals 2. The second one is the golden mean. And the third one is the plastic number. And here we have the pictures of the 2-dimensional lattices, where we are plotting the red node is the point K, and the blue lines, they show the interacting nodes. So as we can see, all of them are local interactions. They only interact with the neighbors. But as we decrease the parameter through these 3 parameters, these 3 choices, we increase the interactions and the density of nodes. Okay, so we have 3 possible products through these interactions. Okay. Okay, now that we have all operations defined, we have derivatives, spatial derivatives, we have product, then we can just write the equations exactly as they are, but taking all operations as we defined above. So if we take all fields, for example, the velocity field or the pressure field, they are defined on the lattice. So they are functions of wave vectors on the lattice, on the logarithmic lattice. Spatial derivatives are Fourier factors. And this is start product appearing on the nonlinearities. These are the discrete convolution we just presented. And we have 3 choices depending on the parameter lambda of the lattice. And we have incompressibility. So the equations are exactly in their exact form. They are exactly as they are in the original model. But just changing the domain, and because the domain changes, the operations are also somehow changed. Okay. Since the equations are in the same form, we can prove using only the operations on the lattice that the model on the logarithmic lattice it retains most of the properties. So the first thing is the group of symmetries. So the symmetries of the Euler equations on the logarithmic lattice are exactly the same as the original model. So we have time translations, space translations, isotropy and parity, scale invariance, time reversibility, and Galilean invariance. The only difference here is that some of them, like isotropy and scale invariance, they are given in a discrete form. So exactly because the lattice itself is not continuous. We can only rotate or rescale again lying on the lattice. So we have only discrete forms of doing that. Okay, but the groups are the same. And also the same conserved quantities. So if U is a strong solution of the 3-dimensional Euler equations on the lattice, we preserve the energy and the helicity for the 3-dimensional case. And in the 2-dimensional case, we preserve energy and entropy, and they are conserved in time. We also have a formulation for the Kelvin's theorem. So of course, here on the lattice, we don't have topology to say what is a loop, but we can take it in a more generalized way. So if we take a frozen to fluid field, which satisfies this kind of convection equation, governing equation, then the cross correlation of the field, of the velocity field and H is conserved in time. And this is exactly a generalization of Kelvin's theorem in the continuous model, because we can take H in this way, and this will give us the conservation of circulation. And this theorem holds for the logarithmic model. So this is what we have for the logarithmic model, and this is an interpretation of Kelvin's theorem in this. And this is important because this conservation holds for any solution of the equation. So this gives us an infinite many conservation laws. Okay. So group of symmetries and quantities are conserved in the same way. And we can also talk about regularity of solutions. So we define functional spaces like mimicking homogeneous Sobolev spaces, HM. So they are just L2 norms of M derivatives. And we also take divergence-free vector fields. And we can show a local existence of strong solutions in this class. So if we take an initial condition in the M, and we can prove that there exists a unique solution of the incompressible Euler equations in this class, satisfying the initial condition. And the solutions blow up in the same way. So we can prove Bialik-Atomaida blow-up criterions, very, very similar. So strong solutions, they blow up in the same way as the original equations. So the integral of the L infinity norm of vorticity from 0 to 2b is infinity in the case of blow-up. And as a corollary, we can show that the strong solutions of the 2-dimensional compressible Euler equations, they exist globally in time, while the 3-dimensional case is the case of interest here. So we can see that the equations, they preserve exact original forms, and also same groups of symmetries and conserved quantities. And with respect to regularity, they behave in a very similar way. But still, we have the advantage of that with only a few nodes, we already span a very large spatial range. So we can simulate them in a computer in an easier way than just with direct numerical simulations, with the full equations. And this is what we get. So we have a numerical evidence of a chaotic blowup in this model, in the three-dimensional incompressible Euler equations on the logarithmic lattice. So here we are plotting two curves in each graph, and the green one is for the golden mean. So it's one of the choices of the parameter of the lattice, and the second one is the plastic number, the red one. In the first graph, we have the time evolution of 1 over the maximum vorticity, and we can see that in a finite time, they go towards 0. This means that the maximum vorticity is growing towards infinity. And this allows us to estimate blowup time. And in the second graph, we have in logarithmic scale the maximum vorticity against TB minus T, where TB is the blowup time. And you can see the scaling of both parameters, the scaling of the vorticity growing as TB minus T power minus 1, which is a clear indication of blowup following Gallic-Atomida criterion. We also observe in the fourth graph here that we have a power law energy spectrum formation in a finite time. So energy goes to k power minus c, where c is 2.26. And we can see a very nice agreement between the two parameters. So it doesn't matter what is the lattice you are choosing, they are always blowing up with the same asymptotic solutions, right? But we can see that there are a lot of fluctuations in the curves, which means that these asymptotic solutions, they are satisfied only in average. And we computed, we show that these are actually chaotic fluctuations. And we can also perform a change of variables. And what we are plotting here is just a structure of high vorticity. So we are depicting only some slices in Fourier space on the three-dimensional picture of the high vorticity structures. So only the higher vorticity is plotted here in colors. And through this change of variables, we show that this blow up is actually is associated with the development of a chaotic wave in Fourier space, traveling with constant average speed through the diagonal. And in the first line, we are showing the time evolution for the golden mean parameter, while in the second, we are showing the plastic number. Because of the plastic number has more interactions, it's more expensive. So this is why we cannot perform simulations for longer time. So, but the golden mean is it reaches a longer time. But you can see that there is a very nice agreement between the two, only up to resolution. Which the plastic number it has a finer resolution because of a higher density of nodes and more interactions. But from these two characteristic structures developed by the model, we conclude the robustness of blowup with respect to the choice of lattice. So from the two choices, we have the same structure developed and with the same parameters. It's also important to notice the size of the structures, because these structures, as you can see, the axis here goes up to 10 power 12. So we can see that the size of the structure is somehow in the order of 10 power 6. If you compare this resolution in spatial range to the available resolution of direct numerical simulations, we can conclude that it's at least from using the techniques available these days, it's impossible to reproduce this blowup of the three-dimensional incompressible Euler equations from direct numerical simulations. And this somehow justifies the controversy about whether there is blowup or there is not. So this also gives us a light in the direction of research, because we should somehow rely upon other criteria. Okay. We can also simulate Navier-Stokes turbulence. So it's very simple. We just take the same equations, the other equations, and add the viscous term here. And from numerical experiments, we can see that it's globally regular as we have a development of a viscous range dissipation, and we can continue the solution for arbitrary times. And we can also verify anomalous dissipation. So what we plot here is the flux, is the energy flux, and we can see for different colors they stand for different viscosities. And here is against is a flux against K, so it's a kind of a spectrum of the energy flux. And you can see that it develops a constant flux, and this constant flux solution is held for it's still in the implicit limit. So we can send viscosity to 0 and keep the constant average energy flux, which is an indication of anomalous dissipation, because we are still going to have injecting energy on the large scales. We are still going to have dissipation in the smaller ones. So we take viscosity to 0 and we have an infinitely large range of constant energy flux. Okay. So also for this model in the Navier-Stokes, in the logarithmic lattice, we can verify anomalous dissipation. And we can go further and look for intermittency. So what we are plotting here is they are the PDFs of some modes on the lattice of the energy of the velocity. They are renormalized for us to check all of them if they are matching or not Gaussian distributions. And we can see here two plots. The first one, they are in the inertial range. So we can see that different colors stand for different modes, rescaled by the same diagonal. And we can see that as we decrease scale, there's still a line on the Gaussian distribution, which is the black dashed line here. So in the inertial range, we don't have intermittency at all, which is in agreement with direct numerical simulations and experiments. But as we go to the dissipative range, we can see that we have this enlargement of tails. So we have a deviation from the Gaussian distribution as we rescale it at finer scales. And this indicates a dissipative intermittency. So for this model, the modes and the modes of the Fourier modes, they behave exactly as the Fourier modes in the Navier-Stokes turbulence, at least from the data we have from the direct numerical simulations and experiments. Okay, so these are essentially the conclusions we address for the Navier-Stokes equations. Now, just to summarize some conclusions. The models on the logarithmic lattice, they preserve the exact form of equations. And because of that, we have the same symmetry groups and same invariants. We have also the same behavior of regularity solutions to the full models, at least for the ones we verified. We checked numerically a chaotic blowup in the three-dimensional compressible Euler equations. So of course, for the original model, this is just a conjecture. And this also, we also show that the blowup may be not accessible to direct numerical simulations because of the large size of the attractor, of the large vorticity structure. We also verify anomalous dissipation in the Navier-Stokes turbulence. And with respect to intermittency, we show that there is a Gaussian distribution of the lattice variables on the inertial range, while we keep intermittent in the dissipative range. And this is also in agreement with experiments. So this also shows that the model is a good tool model for the study of intermittency. Okay. And this technique we presented is ready to use for any PDE with similar structures, so with quadratic nonlinearities. So several examples are available, like natural convection, dystrophic motion, for media, magnetohydrodynamics, superfluids in some models, high-dimensional turbulence, etc. And all the simulations were performed with a library we developed, which is available. And right now we are working on a different formulation, which is the formulation of flows in the presence of boundaries to study possible singularities in the visit limit. And of course, this requires some effort because all the models we presented before, they are developing in a open space, I should say, or in a periodic domain. So here we need a little effort to impose the effects of boundaries and boundary conditions. Okay. So these are the references of the material which is available. And for references, codes, and contact, you may access my website at IMPA. And thank you for the audience, and I'm available for any questions. Thank you very much.
Thank you. Ciro, any questions? All right, so we'll leave to that, and if some other questions appear later, you can still ask Ciro some other time. So let's thank Ciro and all the speakers for the day. Thank them in the name of